Good morning, everyone. Welcome back to our second day of lecture. Today, we're going to continue with the review of um, general chemistry, and then also we're going to begin molecular representations. I think that by the time we get done with molecular representations, we'll be perfectly positioned to take the first exam on Friday. So that is a reminder for you. Um, you have your first exam this Friday, and it will be posted at 8 a.m. and you will have until the end of the day to take that exam. 11:59, it will close p.m. It will close, and it will cover all the information from these last three lectures. Right, the first lecture, which was a review of general chemistry. Today's lecture, which is uh, continuation of general chemistry and molecular representations, and then tomorrow's lecture, which is the end of molecular representations and resonance, actually. And so remember that you do have a test this Friday, and then also on today, actually, will be your first assignment, your first Blackboard assignment, and your first quiz, which will cover the uh, material we covered yesterday, right? The material that we covered yesterday in lecture one. Um, the quiz and the assignment will be posted at the same time, 8 a.m. As the lecture today, and so you will have a chance to complete those. You have until tomorrow morning at 8 or 7:59 a.m. to complete it. Basically, 1 minute before the next lecture, because that's when the next quiz and the next Blackboard assignment is going to be assigned. So just be aware there's going to be one every single day, a quiz, except for on exam days, just to remind you, and then and the day after exam days, and then there will be an assignment after the completion of every chapter that we chapter topic that we go through. All right, so let's get started. Today will be the continuation of general chemistry review and starting molecular representation. So let me change the view here to the presentation mode, and we can get started. Oh, my head's always blocking part of it, but if it makes you feel any better, that part that it's blocking just says continued, right? So I could really just abbreviate it right there, and put continued with a dot, right? Anyway, let's go ahead and go. Oh yeah, and I forgot to also say this. You may have noticed that I've posted on Blackboard the lecture notes, so you can use the lecture notes, like the PowerPoint slides, to take the notes on to make it a little bit easier for you. I do realize this is a lot of information all at once, and you need to take some good notes for your quiz and your assignments. And so I did post the PowerPoint slides for you. All right, let's keep on trucking then. So we begin today doing a review of polarity and dipoles, right? Recall then that we were talking about electronegativity before, and in atoms like oxygen, fluorine, chlorine, those kinds of things, because they're super electronegative. And what happens is that when those electronegative atoms combine with atoms that are not so electronegative, they result in polar bonds, right? Where there's a partial positive on one side and a partial negative on the other side. And obviously, the partial negative side is the side that is the most electronegative, right? So, since those electronegative atoms are so electronegative, meaning they love electrons, they actually do this thing called induction, where they draw electrons away from the or the less electronegative atom, and that induction process actually results in a dipole moment, right? So things that you just need to be aware of here, and we already did this in the last lecture. When we have like a delta positive, that's a partial positive on a dipole moment. And then when we have a delta negative, that is a partial negative on a dipole moment. Dipole moments are actually reported in units of dBis or dBis, and 1 dBi is equal to 10 to the negative 18th electrostatic units centimeters, right? And you'll see where that unit comes from in a second. This will probably be the one of the very few times that we ever do any real math in organic chemistry. So let's take a look at then uh, 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 I keep on calling it methane chloride, but it's actually chloromethane, right? So we have chloromethane right here, and you can actually calculate the dipole moment by using this formula here. Mu, which is the dipole moment, is equal to the charge times distance, right? And this charge here is quite literally the charge of an electron in ESUs, or electrostatic units, and this is literally the bond distance. Okay, so you can do the charge here. So this is a little bit interesting. Okay, the way that we have this example set up. This is not actually the charge of an electron. The charge of an electron is this right here, 4.8 times 10 to the 10 ESUs. But since this is a dipole moment, and we know for a fact that experimentally they have actually measured the dipole moment of the of chloromethane as 1.87 times 10 to the negative 18, right? They actually discovered then that if you use the bond length, which is 1.772 times 10 to the negative 8, as the bond distance, which is actually the bond distance, that is actually this distance right here, right? And you plug in mu as 1.87 times 10 to the 18, which is experimentally measured, right? A scientist, a chemist went through and actually measured that dipole moment experimentally. And you plug it in here for mu, and then you plug this distance here, the bond distance here, for the d, or the distance. You actually solve for the charge, and this is what you get for the dipole moment of sorry, this is what you actually get for the charge difference in the dipole moment, right? So knowing that, and knowing that mu here is the dipole, which is 1.87 dBs, remember that one dBi equals 1 times 10 to the negative 18 ESU centimeters, right? We can convert that to dBis just by saying 1.87 dBis. So I know that was a little confusing, but let's go on to the next slide. It'll come together in a second. You can actually take the actual charge in an electron here, right, which is 4.8 times 10 to the negative 10 ESUs, right? Multiply that by the bond distance that we were talking about a second ago, right? And then you'll get a mu, or a formal charge, of 8.85 times 10 to the 18, right? Or we can convert that to dBis there, okay? Or 8.15 dBis, okay? So this, when you use the actual charge of the electron in the equation, along with the actual bond distance, right? And you get this number, the 8.51 dBis. That is representative of a bond that is 100%. Forgot to put the 100 part. 100% ionic. Right? It's a bond that's 100% ionic between the carbon and the chloride, right? Or the chlorine, okay? So when they did the experiment and they found out what the actual mu was, or dipole moment was, they found that it was actually 1.87 dBi, right? And that's how we were able to figure out before that the actual charge difference, right, is 1.056, right, by back calculating that. So what that does for us then is that, let me move my head out of the way real quick so you can see this calculation. You can actually take the actual measured, experimentally measured dipole moment, which is 1.87 dBi, divided by the calculated, based on an electron's charge, 8.51 dBi, times it by 100%, right? And you'll get 22%, And what that 22% means is that this bond, in fact, is not 100% ionic. It only has 22% ionic character, right? And what that means then is that the bond between chlorine and carbon and chlorine is actually mostly covalent, right? So that's all that really means. So doing these kind of this calculation, you can figure out whether or not a bond is truly covalent, right, or mostly covalent, and how much ionic character that a bond has. Okay, and you may be asking yourself, where do we get these numbers too? Well, you can get the charge of an electron from a table in our textbook. You can also get the experimental, this number right here. Oops, the experimental dipole moment here from a table in our textbook as well. There's actually also this this other thing here called the CRC, and I have, well, you know, I have a very old version here, 1987's version, right? Super old version, because CRCs are actually super expensive, but it's the handbook of physics and chemistry constants, and different values and such, experimental values, and you can actually find those numbers in here too. So in any case, right, that's how we figure out whether or not a dipole or a bond is, what the percentage of ionic character it is, and whether or not it's mostly a covalent bond. So in doing that, we can actually do we have charts here, a chart here that shows the percent ionic character for several different bonds of things that we know. For example, a CO bond, single bonded CO, or a OH bond, or a carbonyl bond, right, or a double bonded carbon to oxygen bond, right? And again, we just do the same calculations as before. This number here is for all three of these different bonds, this number is the experimentally measured value of the actual dipole moment, right, or mu. And then down here is the actual charge of an electron, right, multiplied by the bond distance between the two atoms, right? And that gives us, and when we do this calculation, that gives us a percent character of the percent ionic character of each of those different bonds. So again, let me move my head out of the way real quick so you can see the rest of this here. You can see that on a carbon-oxygen single bond, right, it is only 10% ionic character, which means that is mostly covalent, which makes sense. We get a little higher here with an OH bond with 33%, but then we have a carbon double bond oxygen, which is 41% ionic, right? So that's the least covalent of all of them, or the most ionic of all of those three. So if we keep on moving forward, we should ask the question then, why is the percent ionic character? You see, these are the same again on this chart here. These are all the same again on this chart here, right? But the question then is, why is the double bond carbon oxygen double bond so much more polar than the single bond? Well, it really does come down to the bond distance, right? We talked about this before in the previous lecture, where when you had a carbon oxygen, when you have a single bond, it's the shortest, or a sigma bond, right? It's the shortest. And then when you have a double bond, I said that backwards, I apologize. When you have the single bond, the bond is the longest, right? When you have a double bond, you have the bond even shorter, the distance between the two atoms even shorter. And then when you have a triple bond, it's even shorter than that, right? So when you look at a carbon-oxygen single bond, its bond length is 1.4 or 1. Whereas when you look at carbon double bond oxygen, its bond length is 1.227, right? And when you plug these into the equation, right, you actually end up with a smaller number at the bottom for the calculated dipole moment. And when you have a smaller number divided by a number, right? Excuse me. When you have when you have a smaller number divided by a numerator, that doesn't make sense. When you have a numerator divided by a smaller number, the larger the answer will be, right? Mathematically. And that's why you have a 10% dipole moment, a 10% ionic character for the single bond, and you have a 41% ionic character for the double bond, right? So that's the mathematical explanation. The chemical explanation is that the closer the bond is, right, the more it can draw away electron density from the carbon, right? And the more it does that, the more electronegative it is on the electronegative side or the partially negative side, and the less negative it is on the carbon side, right? So that makes a lot of sense, both chemically and mathematically. Let me bring myself back. There we are. So then you take a look at molecules that have more than one bond, right? And when you have more than one bond that are polar, it is actually the sum vector, the vector sum of all the individual bonds that indicates what the dipole is, right? So here we have dichloromethane, right? So 2 chlorines on a CH2, okay? And you have then the the partial positive going towards the, partial negative going towards the chlorines, right? Well, what is the net sum, the vector sum of all those individual bonds, right? It means that the dipole moment is in this direction, right? It's going towards the chlorine atoms, right? Going toward the chlorine atoms in that vector sum. Same thing is true then of pneumonia right here. The nitrogen is the most electronegative, right? So it's going to be drawing electron density away from the hydrogens towards itself, right? But then you have a lone pair up there, because nitrogen does have a lone pair, which is the most electronegative because it is actually electrons, right? And so then the electron density gets pulled towards those lone pairs, so your net dipole moment has it pointing upwards from the hydrogens towards the lone pair. And then the same thing is true of water. You have water here with its super electronegative oxygen in the middle, drawing electron density from the hydrogens towards it. But then water also has those 2 lone pairs at the top, which are also in itself electronegative, right? And so it draws electron density up towards the lone pairs, and so your total net dipole moment, it goes upwards towards the lone pairs on oxygen. So the thing about it is that for you to be able to actually determine or analyze a certain molecule to figure out what its dipole moment is, net dipole moment is, you really need to know what its geometry is, right? And remember, we figured out that before that ammonia was a trigonopyramidal, pyramidal, right? And the thing that was at the very top of the pyramid was this lone pair of electrons. So you can see just from the geometry of it that the electrons are actually being drawn towards the tip of the trigonal pyramid, right, of ammonia. Take a look at water, though, right? Water had the bent configuration, the bent geometry, and it's bent, right, because it had the oxygen connected to the 2 hydrogens, but they're bent down because they have the 2 lone pairs also at the top, right? 2 lone pairs also at the top. So the question then becomes, would the dipole moment of water be different if it was straight instead of bent, or linear instead of bent, right? Well, the answer to that is yes, because when you have, it's almost like this bent is almost like the pyramid thing, where you have the electron density being pulled towards the tip of the pyramid, or in this case, the tip of the bend, right? And so you have a net dipole moment going upwards toward the lone pairs because it's at the tip of the bend, right? But if you were to have just, this is not real, right? But the only way that water could not be bent is if there were no lone pairs there at all, right? No lone pairs there at all, okay? So it's not bent. So now the vectors are going towards the oxygen. And in fact, they cancel each other out, right? So when they cancel each other out, you actually end up with a net dipole moment of 0. So geometry actually does make a big difference when it comes to being determining a dipole moment for a molecule. Okay. So we can actually take a look at these electrostatic maps to show us, how how polar. There he goes. I was like, how do you say polarity in like the small word, polar? So yeah, so you can actually take a picture or take a look at these electrostatic potential maps, right? To evaluate the polarity or see how polar a molecule actually is. So here again we have dichloromethane, right? We know that the net dipole moment is pointing towards the most electronegative thing on that on the molecule there, which is the chlorine and its lone pairs, right? So you can do a mathematical calculation using some computational chemistry, which I used to do a lot of, and it actually detects that the vast majority of the negative part of this atom, the partial negative, is up there towards the chlorine, while it's mostly positive down at the bottom, right? Based on this little key we have here, right? And you can actually apply that kind of electrostatic potential map to any molecule, right? I used to do it on like big amino acids and different protein structures, and they get pretty complicated, but they help you see a lot of things. So polarity and dipoles, right, actually have a lot to do with solvents, right? What can dissolve something else, right? Like how water can dissolve salt or something like that. Okay, so let's just quickly look at a little table here of some different solvents, and then we'll apply that to something. Okay, acetone here has a dipole moment of 2.8. Acetone has a dipole moment of 2.69. Sorry, it's a little small on my screen for some reason, which means it's probably small on your screen too. Maybe I need to make it bigger. Dichloromethane here, another organic solvent, has a dipole moment of 1.87. Water has a dipole moment of 1.85. Methanol has a dipole moment of 169. Ethanol 166. All these guys are actually very close to each other right here, right? So they're miscible. Okay, they're absolutely miscible in each other. Those will actually dissolve in with another, and you know that already, right? Because when you drink alcohol, it's never 100% alcohol. It's usually mostly water. Like beer is like 7% alcohol. Everclear is like 95% alcohol. Well, what is the rest of it? It's water. Ammonia, 1.47. Diethyl ether right here, 1.15. We have pentane here that it has actually a dipole moment of 0, which makes sense. There aren't any electronegative atoms connected to that at all. It's all carbon. It's all organic, right? Organic hydrocarbon to be exact. So it has a dipole moment of 0. And then also we see here we have I forget what we call this. Oh, carbon tetrachloride, right? So carbon tetrachloride actually looks like a normal carbon, right? Actually, it looks like methane, except instead of having hydrogens all the way around at 109 degrees, it's got chlorines all around at 109 degrees. Okay, and then since these are all equivalent chlorines, the partial negative charge is being pulled towards each of the chlorines, right? So there's actually a partial negative on each of these charges, on each of these chlorines. Okay, and they all cancel each other out, right? Because, well, they don't really cancel each other out, but they show that the net sum, the sum of the vectors, the net sum of all the vectors of the dipoles are actually going equally in all directions around the carbon, right? And so there really isn't a dipole, right? Because there's not one side that's more polar than the other side, or sorry, more negatively charged or more positively charged than the other, right? And that's why carbon tetrachloride has a dipole moment of 0 as well, right? So you can practice some identifying the presence of dipole moments, right? using the Skill Builder 1.9 in Wiley Plus. So make sure you check that out, right? I feel like I'm plugging in like advertising for Wiley Plus, but it really is a helpful resource. So put a pin on that thing about common solvents. We're going to get to that in a second, right? Let me get a quick drink here. Speaking of solvents. So there are many intermolecular forces that are not covalent. Okay. In fact, when you get to biochemistry, you talk about the 4 intermolecular forces that are not covalent that actually keep proteins together. And we are going to dive into those here right now, right? Because it turns out that organic chemistry is the basis of a biochemistry, right? Of biochemistry. So we're all connected with each other. So let's just read this real quick. Many properties such as solubility, boiling point, density, state of matter, melting point, etc. are affected by interactions that are between separate molecules. So just in case you don't know, we have the intermolecular forces, right? And then you have the intramolecular forces. So inter is between molecules, intra is inside of a molecule, okay? So neutral molecules, polar and nonpolar, are actually attracted to one another through these intermolecular forces that are not covalent. Okay, they're not covalent because there's no sharing of electrons. They're just they're sometimes fleeting, they're ephemeral, right? But they're not covalent and they're intermolecular, right? We have the dipole-dipole interactions, the hydrogen bonding, and the dispersion forces, which my favorite is London dispersion, right? We do a lot of all 3 of those in biochemistry. Don't forget that pin I told you to put in about solvents. So the first one, right, let's go through each of these individually now. The first one is a dipole-dipole interaction, right? And the dipole-dipole interaction is quite, simple and easy to understand. When you have 2 magnets, right, and the 2 magnets are both positive on one side and negative on the other side, or north on one side and south on the other side, right? And you pull them together, what happens? The north side is attracted to the south side, right? The same thing is true here. When you have 3 molecules right here that I think that's acetone. I can't tell what it looks like in there. But when you have 3 molecules of acetone, right, and you could have a gazillion molecules of acetone, for that matter. But when they're all lined up with each other, right, the negative sides are attracted to the positive sides. And the negative sides over here are attracted to the positive sides. So a dipole-dipole interaction is literally the attraction between the partially positive side of a molecule and the partially negative side of the molecule, right? Just like it is in magnets. It is acetone. I was right. It says acetone right there. So acetone has got a permanent dipole, right? Because it's by nature of its structure, it's permanently dipole, right? With the oxygen on the one side and the methyl groups on the other side. All that electron density is being pulled towards the oxygen at the end of the double bond, right? And so it's got a permanent dipole, and that permanent dipole makes it so that acetone is attracted to each other through the dipole-dipole interactions, right? So this says here, the dipole-dipole attraction between acetone molecules increases acetone's boiling point and melting points, while similar molecules without dipole-dipole interactions, such as isobutylene, right, which is actually which is a hydrocarbon, right, has a lower boiling point and lower melting point, right? So what that statement is saying then is that when you have some of these, not just dipole-dipole moments, but all of the intermolecular interactions, right, the more of them you have occurring, the higher the boiling point and the higher the melting point. And that makes sense because when they're more attracted to each other, they're not going to break apart, right? Quite literally, when you melt something or you are boiling something, you're separating the molecules from each other. Like when you're boiling water, you're actually vaporizing the water molecules, and they're going into the air, right, as water vapor, and they're just singular water molecules, water vapor molecules, H2Os, right? But they're not being attracted to each other because you've boiled them, right? And you've broken one of the next ones we're talking about is we've broken the hydrogen bonding interactions between the water molecules, right? So that's the thing that you need to remember right here. when you have the more of these interactions, especially in this slide right here, the more dipole-dipole interactions you have, the more likely the molecule will stick together, right, and stay in its state, whether it's liquid or solid, right? And the fewer the dipole-dipole interactions you have, right, the lower the melting point is, the lower the boiling point is, right? So the less likely it's going to stay in its state at lower temperatures, right? So what does that mean then? You need more energy to vaporize or to separate the molecules of acetone, whereas if you were to compare that to isobutylene, which is hydrocarbon, right, made of carbon and hydrogens, right, it would take less energy to break apart those, boil those, or melt those. So here is the actual experimental proof of that, right? We have isobutylene right here, what I was talking about before, which is the hydrocarbon. Hydrocarbon meaning a molecule made of only hydrogens and carbons, right? And its melting point is below freezing, negative 143. And its boiling point is below freezing, negative 6.9 degrees Celsius, right? Man, that's, I mean, it can't even exist in like normal temperature and pressure, right? Like in our, it does exist. I'm sorry, it doesn't exist in its liquid or solid phase, right? It's always a gas at our comfortable, environment, an environment that's comfortable for us. But then you take a look at acetone, right? Which everybody knows acetone as nail polish remover. I use acetone a lot too because I think I told you before I do a lot of 3D printing, and acetone vapors actually go through and smooth out 3D prints using the vapor, because ABS, which is a plastic you can use to 3D print, is the same plastic that's used in Legos. It interacts very well with acetone, and it makes the prints very smooth. But anyway, sorry, off topic. Check out its melting point. From solid to liquid is at negative 94.9 degrees Celsius, right? And which is still like below freezing for us, below freezing temperature of water. But the boiling point here is the more important thing here, where its boiling point is 56 degrees Celsius, right? And that's all because of this dipole-dipole interaction that can occur between acetone molecules, holding them closer to each other. So, like I was saying, this next one is hydrogen bonding, right? And I was just talking about before about hydrogen bonding in water, and you can see down here, water, is an oxygen connected to two different hydrogens, right? So, what hydrogen bonding is, in its essence, is the bonding between a hydrogen that is connected to an electronegative atom. In water's case, it's oxygen, right? And then that hydrogen bonding occurs when it's attracted to the lone pairs or an electronegative atom of another water molecule or another electronegative atom, right? So the key here is that hydrogen bonding in this attractive force only occurs when you have a hydrogen that is covalently connected to another electronegative atom, right? And then that hydrogen that's already covalently connected to another electronegative atom, like an oxygen, right? That hydrogen is then attracted to the partial negative of another electronegative atom that it's not connected to at all, not covalently, right? And so that right there is called the hydrogen bond. Let me clear this real quick. I don't know why I drew those arrows. So that right there is the hydrogen bond, right there. See, you see that this hydrogen here is connected covalently to this oxygen, right? Why does it do that? Why is that important? It's important because this electronegative oxygen, right, is pulling electron density away from the hydrogen, making this hydrogen partially positive. That partially positive hydrogen is then attracted to the partially negative electron density of another water molecule, which is this oxygen with its lone pairs right here, right? And that is what forms a hydrogen bond. Okay? It doesn't have to be oxygen. It can be any electronegative atom, right? Nitrogen, fluorine. We see it actually a lot in nitrogen, and we'll see it a lot in nitrogen in a second. But here is an ammonia, right? Here's an ammonia. And again, the electronegative nitrogen pulling electron density away, causing a partial positive hydrogen right here that is attracted to, right, to the electron lone pair, the lone pair of electrons on another ammonia, right, because that is the partial negative side of the ammonia molecule, right? So again, just to be clear, hydrogen bonding can only occur when you have a hydrogen that is covalently bonded to an electronegative atom, making that hydrogen partially positive. So now it's attracted to the partial negative of another electronegative atom that also has a hydrogen on it on the other end too, right? So that's hydrogen bonding. And I don't know if you noticed this, but it really is another type of dipole-dipole interaction, because the hydrogen is a dipole, right? The hydrogen is a partially positive, and there's a partial negative oxygen, right? And that's in itself a dipole, and that dipole is attracted to another dipole, right? So it is a dipole-dipole interaction. It is a type of dipole-dipole interaction that is especially strong, right? And you'll see how strong it is in a second. So here's some other examples of hydrogen bonding. So here we have ethanol, right? And ethanol is hydrogen bonding to another ethanol, right here, right? Because of the same thing I just said before, okay? But so the interesting thing about this is that hydrogen bonds are still, even though they're super strong, they're still 20 times weaker than covalent bonds. Oh, sorry, that's my head's covering what that says. That says about 20 times weaker, right? Than a covalent bond. So solvents that engage in hydrogen bonding, right, are called protic solvents. And then solvents that do not engage in hydrogen bonding are called aprotic solvents. Okay? So, like I was saying before, we have here acetic acid, and there is a hydrogen bond capable of happening right there, right, with other acetic acids. So that's why it's a protic. But then when you look at things like dimethyl ester, none of those hydrogens right there are connected to an electronegative atom. So that's why it's aprotic. It doesn't participate in any hydrogen bonding. And then we have dimethyl sulfoxide, also aprotic, because none of these hydrogens are connected to anything that's electronegative. Right? So that's the difference between a protic and an aprotic solvent. Keep that in mind. So hydrogen bonding also is important in constitutional isomers, right? We were talking about isomers before, where they have the same molecular formula, but they're connected differently, okay? Take a look at trimethylamine. Just like in dipole-dipole moments, the more hydrogen bonding you have, the higher your boiling point and melting point are, or melting point and boiling point is. So when you look at trimethylamine, none of these hydrogens are connected to directly the nitrogen, which means trimethylamine cannot participate in any hydrogen bonding, and its boiling point is 3.5 degrees Celsius. Let's take a look now at ethylmethylamine. Why is it ethylmethylamine? We have an ethyl there, we have a methyl there, and then we have an amine group, right? So, but notice that though one of the hydrogens here is actually directly connected to the nitrogen. So it can participate, though limited, it still can participate in hydrogen bonding, because hydrogen is directly connected to an electronegative atom. In the case here, it is nitrogen. So that increases the boiling point by like 30 degrees, 40 degrees, because its boiling point now is 37 degrees Celsius. 37 degrees. Isn't that 98.6 degrees Fahrenheit? Isn't that our body temperature? Well, that's interesting. Now let's take a quick look at propylamine, right? Propyl, because it's a propyl group right there. Propyl means 3 carbons, right? Connected to an amine. Don't worry, we'll go through this a lot later, like naming atoms. Naming organic compounds and such. Notice it can participate in 2 hydrogen bonding. Well, not participate, but it can really participate in hydrogen bonding, right? Because it has 2 hydrogens connected to the electronegative nitrogen, right? Which means then that it can actually have another propylamine over here. I'm trying to draw this out right here. Nope, too many carbons there. We only need 3. There we go. And then you can have another one here. One, two, wait. 1, 2. Let me just try that again. There we go. I actually just had 1 extra carbon on that one over there. That's what it was. Drawing too fast. Getting ahead of myself. There we go. So when you compare it to ethylamine, ethylmethylamine right here, which can only, excuse me, which can only do it to, let's see here, let me see if I can draw this here. Can only do it to 1 at a time. All right. Propylamine can hydrogen bond to 2 at a time, so that means it can participate in more hydrogen bonding than ethylmethylamine. And the more hydrogen bonding you do, right, the more the boiling point you have, the higher the boiling point, which is 49 degrees Celsius here, right? So takeaway from that is, just like dipole-dipole interactions, the more hydrogen bonding you participate in as a molecule, the higher your boiling point and the higher your melting point too. So I was talking about DNA before and proteins before and all this other stuff. Hydrogen bonding actually plays a huge part in DNA, right? And in proteins. So what you actually see here is an alpha helix. And an alpha helix is actually a secondary structure that gets formed from amino acids, right? Before it becomes a tertiary structure that is a functional protein, okay? And alpha helices are formed when amino acids, which we'll talk about later, but amino acids get together to make this polypeptide chain, and then they fold, and when they fold, hydrogen bonding happens between these amino acids in such a way, in such a pattern, right, that it makes the entire chain of amino acids spiral in the shape called an alpha helix, right? Called an alpha helix. These are all hydrogen bonds in between the different spiral sections of an alpha helix, okay? And we won't go into too much detail on that, because there's a whole section about biochemistry at the end of organic chemistry. And some of you are actually going to go off to biochemistry, the class I love teaching, and actually learn in excruciating detail the interactions that are at play when it comes to amino acids and their amino acid chains or peptide chains. Also, in DNA, right? This is DNA over here. Deoxyribonucleic acid. And the thing that makes the rungs of a DNA ladder are called nitrogenous bases, right? If you recall from biology, A goes to T and C goes to G, right? So that's adenine attaches to thymine, and then cytosine attaches to guanine, right? In DNA over here, in the ladders of the rungs of the ladder of a DNA double helix, right? And it turns out that when you have an A on one side of the rung over here, and a T on the other side of the rung here, they're actually connected to that ladder, in that ladder making that rung with 2 hydrogen bonds. Okay? If you look at another rung, and one side is a G, and the other side is a G, a guanine and a cytosine, they're actually held together with 3 hydrogen bonds. Right? Does that make sense? So that actually has a lot of implications in molecular biology, right, and in biochemistry work, because you can actually do this analysis where you talk about the GC content of different DNA, chains, right, or DNA compositions. Sorry, composition genes. There we go. The GC content of a gene, right? And so it turns out that when you have too much GC content, right, these hydrogen bonds right here, 3 of them, they're so strong, okay? And so when you're doing molecular biology, one of the things that you need to do when you do this thing called PCR, polymerase chain reaction, is you need to unzip the DNA using heat, right? And when you unzip the DNA using heat, what you're essentially doing, like I was telling you before, is breaking those hydrogen bonds with heat, right? And you can just use water as an example. How much energy or how much temperature, what temperature do you need to actually make water break its hydrogen bond to vaporize? You need at least 100 degrees Celsius, right? It's very similar with the hydrogen bonding inside DNA. You need like 95 degrees Celsius to break those hydrogen bonds, right? But the problem is that if you have too much GC content, like the GC content is like over 30% or maybe over 50%. The hydrogen bonding there's so much of it, right? That it holds together super tight and you can't break it apart. And when you can't break it apart, you can't access the gene. You can't make copies of the gene, right? You can't amplify it so you can put it into your own vector, right? And make your own copies and translate your own proteins from that gene. So GC content is actually a very important concept in molecular biology and doing molecular biology work. Okay, and I just briefly talked about PCR, not supplement, but that's again beyond the scope of the class. So what I want to end this slide by saying is that on its own, a hydrogen bond or even a dipole-dipole interaction, right, on its own it's not very strong. But when you bring a whole bunch of them together and they're all acting together, it can be substantially strong, very strong. Okay. So these are also being held together by London dispersion forces too, but we'll talk about that in a second. Oh, we'll talk about it now. So what are London dispersion forces? Well, London dispersion forces occur. They're also a type of dipole-dipole interaction, but it's more of an ephemeral one or a temporary one, right? Because it only occurs between atoms that have, molecules that don't have a dipole-dipole moment, right? So like a complete hydrocarbon, for example, like a butane, 2 butane molecules, right? 4 carbons, all covered in hydrogens, no other molecules, no electronegativity, right? And but they can still be attracted to each other, even though they don't have a permanent dipole-dipole interaction or dipole-dipole moment. But they can have temporary dipole-dipole moments too, because when you think about a molecule, right? I think that many students have this problem where they think that a molecule or even an atom is a static picture, where there's like protons in the center, neutrons in the center, and then electrons zipping around in these like paths that are defined around the atom or the molecule for that matter, right? But the truth is, inside of a molecular orbital, that electron can be anywhere, right? It's not just zipping around like in a circle around an atom, like those pictures that we see in like elementary school, right? They can be anywhere where the molecular orbitals that are determined by the wave function, right, show that their density, electron density is, right? And they're probably, like I said in the last one, right? I said 99%, you know, that's where they are. But really it's 90 to 95% because we really don't even know, right? For sure. And they can be anywhere around there, right? And so when two butane molecules come to close to each other, and all these electrons are just floating around randomly in their like molecular orbitals, right? Just all over the place. It's very dynamic, right? They're all over the place. And two butane molecules come close to each other, right? Well, those electrons start to like disperse each other because of repulsion, right? Because two negatives repel each other, and when it does that, it exposes the carbon centers, right? A little bit, the partial positive carbon centers a little bit, making it kind of positive a little bit, right? And so electrons get to be more from one molecule of butane gets attracted to the temporarily exposed carbons, right? Because we already said before that carbons are generally partially positive, right? And so that causes very slight, very weak intermolecular interactions that are formed from temporary dipoles, right? And that's what a temporary dipole is. A temporary dipole occurs when the random distribution of electrons all around a molecule get dispersed to different areas, exposing some positivity, not a lot, but some positivity, making them attracted to each other, right? So that's what a London dispersion force is. And I'm sure there's a picture of this on the next slide. I didn't have to explain it all just by my hands just now. Ah, there it is. Oh my god. Well, this is not a butane molecule. This is a pentane molecule, right? This is a pentane. But same properties as butane. Completely hydrocarbon, right? No permanent dipole, right? But what happens is that all these electrons and all this density here, right? All these electrons that are floating around, you know, in their molecular orbitals, right, will bounce around and start repelling each other when they get close to each other to another pentane molecule. And what happens is that it exposes some of the carbon over here, right? A little bit of partial positive from that carbon over there, and then that gets attracted by the partial negative of another butane molecule that had its electrons pushed to one side by another butane, right? And or pentane. And you can see how this is like a cumulative effect. When it all adds up together, you can have some pretty strong London dispersion forces. Okay, pretty strong London dispersion forces. Like I said before, it's fleeting, which is ephemeral. It's temporary. They're generally weak, but like I was saying, you know, even though they're weak interactions, if there's a whole bunch of it, it can add up to be very significant, very strong. So strong, in fact, and I didn't even know this, right, that it turns out that geckos have on their feet, right, little hairs, right, that they use to attach to like glass, you know. Like I have a gecko in my fish tank over there, and I could show it to you, but my studio is not movable. It's not mobile. But, you know, he's sticking on the side waiting for me to throw in like a roach for him to eat, right? And the way he's sticking is that he's got little little hairs on his toes or feet, right, that are attracted to the glass through London dispersion forces. Had no idea. It's crazy stuff, right? Maximize surface contact, right, with their feet and flexible hairs, right? The resulting London dispersion forces are strong enough to support the weight of a gecko. Who would have known? Oh, that David Klein. He's always putting in interesting facts in his stuff. But let's do something more chemical. I mean, that was a kind of a biological example, but let's think about this in more chemical terms, right? I was just talking about butane right here, right? And butane is going to participate in London dispersion forces, right? But, right, it's kind of a short molecule, so it's got less surface area. So its boiling point is 0 degrees Celsius, because that less surface area makes it difficult for you to, not difficult, but makes it less likely that you form a lot more London dispersion forces, right? But we move up to pentane. Pentane's a larger molecule, right? So it can do more London dispersion forces, right, than butane can. And so its boiling point is 35 degrees Celsius. And then we have hexane. Hexane's at 69 degrees Celsius because it's even got more surface area. So the point here is that when a molecule is participating in London dispersion forces, right, the more surface area it has, the more London dispersion forces it can participate in. And what that means then is that it can hold itself together longer and better. It requires more energy to break those London dispersion forces apart, which means it gives it a higher boiling point. And it's the same principle as it is with hydrogen bonding, as it is with dipole-dipole moments, those three, right? The more of each of those different kind of interactions, the more stable the molecule gets at certain temperatures, and so the higher the boiling point, higher the melting point, right? So, practice with some skill builder on 110, right? Predicting physical properties of compounds based on their molecular structure. That sounds like a good time. Feel free to go over to Wiley Plus to do that. Excuse me. So, it turns out, though, that when hydrocarbons branch, right, which means that they don't do the straight line anymore, but they branch off and make these branches like this over here, right here, right, it actually decreases their surface area, right? And when it decreases their surface area, like 2,2-dimethylpropane right here, right, it actually lowers the boiling point. And that makes sense too. That's just understanding, right, the fact that when you have something that's completely rolled out and flat, it's got more surface area than something that's completely crumbled up, right? Think of a foil. You can roll out a foil, right? Say a 1 foot by 1 foot foil, sheet of aluminum foil, right? And put it onto your thing so you can bake your pizza in your oven, okay? So you have 1 foot by 1 foot surface area of that foil on one side, and then you have 1 foot by 1 foot surface area of that foil on the other side. That's a lot of surface area, right? I don't know if a foot pizza is big enough for me now. I usually get 16-inch pizzas. Is that large or is that extra large pizza? I don't know. But then if you take that foil and you crumple it up into a little ball, right, that surface area diminishes greatly, right? It is tiny now. It's so much smaller now. And if you were to calculate the surface area of that ball of foil compared to the aluminum foil laid out, right, it'd be like 1 inch by 1 inch by 1. If you were really strong, you could squish it to really small, right? 1 inch by 1 inch by 1 inch by 1 inch, you know. I mean, that's a very small surface area, right? If it were a 1 inch diameter ball of foil. And the same thing is then true of molecules, right? A molecule like pentane that's completely unrolled, flat, straight chain carbon, right, has more surface area than a balled up, branched hydrocarbon like 2,2-dimethylpropane, right? Or even a partially balled up molecule like 2-methylbutane, right? So we were talking. Remember, I told you to put a pin in solvents and stuff like that. Well, now we're going to talk about solubility, polar versus apolar, right? Or polar versus nonpolar. I don't know why they say apolar there. Let's just use the word nonpolar. Okay. There's this. So chemistry is weird because in general chemistry, it was like opposites attract, right? Where you had cations on one side of the periodic table, and you had anions on the other side of the periodic table, right? And they were opposite charge, and they came together to make molecules, right? Because opposites attract, okay? Well, we're here in organic chemistry now, and the new phrase is like dissolves like, or like seeks like, or like likes like, right? And what that means is that the more alike two solvents are, the more likely that they are mixable in each other. They'll dissolve in each other, right? It's not just two solvents, but a solvent and a solute, right? A solvent and a solute. So what's a good example of that right now for example, a polar solvent, right? Well, water is a polar solvent, okay? What can it dissolve super well? Water can dissolve salt really well. I know for a fact I have a saltwater fish tank, right? Why is that? Well, because sodium chloride is also very polar, right? Sodium chloride, right? I don't know what happened there. That's my pen messed up. I just blame everything on my Apple Pencil because, you know, what else am I gonna do? Sodium chloride, right? It's negative on one side, positive on the other side. Okay. H2O, right? I don't know why I wrote it out like that. I should have just drawn it like this, right? And it's definitely negative on one side. It's partially negative on one side, partially positive on the other, right? So those solvents are actually very alike, right, in their polarity. And when they're alike in their polarity, one can dissolve the other, right? And literally, what will happen is that the partial negative oxygen will surround the sodium ions, and then the partially positive hydrogens will surround the negative chloride ions, right? Did I say that right? Let me say that again. Partially negative oxygen side, right, will surround the sodium ions because it's positive, and then the partially positive hydrogens will surround the negative chloride side because it's negative, right? And that's how it dissolves it, right? So when you have similar polarities, you can dissolve it. You can dissolve things, right? And I know that it says here like dissolves like, but really it should be likes. That's not right. Likes like. Right? Likes like. Which means that a solvent that is alike with a solute likes each other, right? I had a friend in grad school that was actually doing a lot of research on solvents, and the way he said it was like seeks like. So a molecule will see a molecule will seek another molecule that's like itself, right? So the same thing is true then of nonpolar molecules, right? So if you take something like pentane or butane, right, it's not going to want to dissolve in water because it's completely nonpolar, and water is polar, right? But if you take pentane and you try to dissolve it in some methane or some, well, that would be hard because methane is not liquid at room temperature. Hexane. So you take some pentane and you try to dissolve it with some hexane, it will dissolve because those two have similar polarities, right? So two things that have similar polarities will like each other, and in essence generally dissolve in each other, or one will dissolve the other, right? That's actually an important thing to think about too when you get to like organic chemistry lab, because you'll be doing a lot of things like with separating molecules like in a separatory funnel, like your compound, your products and stuff like that. And so generally you'll have like a solvent layer, like a polar solvent layer, which is the water. It's usually at the bottom. It depends on the density, right, of the solvents. I mean, non-polar and polar solvents can have all wildly different densities. But say the water is the most dense one, and it's at the bottom of the separatory funnel, right? I'll just draw it out for you here. A separatory funnel is literally a funnel that looks like this. So this is the funnel part down here, right? And it's got a lid at the top. So it's a funnel with a lid at the top is what it is, okay? And you can put in a mixture of two solvents, right? And then you'll have two layers. You'll have a layer there, maybe it's water, and you'll have a layer here, maybe it's we'll just say hexane for the hell of it, right? Because it's something we've talked about before, right? And it will actually separate in the separatory funnel, and then you can open up the separatory funnel and let the water come out, right? But leaving the hexane behind, and your molecule, your product, right, will be like either the water in polarity or like the hexane in polarity. And so where do you think it wants to hang around? Where it's like, right? So say your molecule, your product that you produced, right, is nonpolar, then it's going to be more likely be in the nonpolar layer of the hexane, right? So you let the water drop out of the funnel, then you close the valve, right, and then all you have left in the separatory funnel is the hexane that contains your product, right? Which is great because hexane has a low boiling point. You can evaporate off all the hexane, and then you have your product, right? Good stuff. You'll be doing that in lab later on this semester. So then, let's talk about something very practical here, right? We know that things like oil don't do well with water. Like you can't mix water and oil together. I mean, think about a vinaigrette, right? Like Italian dressing or something, okay? They're not miscible with each other, okay? Because oil is this molecule here. This is known as a fatty acid. Oops. Fatty acid, right? And it has a polar group on this side, and it has a non-polar group on this side. This polar group here is actually called a carboxylic acid. Carboxylic acid. A carboxylic acid is quite literally a carbon with a carbonyl, right? And then an oxygen connected to, with an oxygen connected to it, right? And it's called an acid because it has a negative charge here. But the reason why it has a negative charge here is because it actually can lose a proton. And that proton usually is what's on the negative oxygen, right? And that's why it's a carboxylic acid. And then down here, you have this nonpolar group here. I think this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's interesting that they would use a 14 carbon fatty acid. Why wouldn't they use a 16 carbon fatty acid? Palmitate, right? Palmitate is actually the most commonly made fatty acid in your body through like fatty acid synthase. And also, it's also the one I know the best. So why would they not? You know, because I don't know what the 14 carbon fatty acid's name is. Anyway, right? So that's a fatty acid. But you can see though that it's mostly, the fatty acid is mostly this nonpolar group right here, right, of hydrocarbons. And that's why it can't dissolve in water. That's why you can't, you know, just use water to wash your dishes after you've had a greasy meal, right? So what do? You use soap. So soap, right, actually is another molecule that's called sodium, a type of soap anyway, known as sodium dodecyl sulfate. Right? Like if you look on the back of molecules, on the back of soap, or even shampoo, you look at the list of, you know, ingredients that you can never pronounce. One of them is actually sodium lauryl sulfate, right? It's the same thing as sodium dodecyl sulfate. It literally makes bubbles, right? It's a soap. And the reason why soap molecules can help you in the destruction of oil and grease on your pans and on your plates, right, is because it will form this thing called a micelle, right, where the sodium dodecyl sulfate actually looks a lot like the oil, the fatty acid, right, where it has a very polar polar group on one side and a non-polar group on the other side, right? And when it does that, due to hydrophobic effect, which is another another non covalent intermolecular interaction, right? All the fatty tails, or the long chain carbon, right? 14 carbons long in this case, I guess, because that's what they drew in the previous slide, right? Due to the hydrophobic effect, they all want to come together, right, and protect themselves from the water, because it's called the hydrophobic effect. And when they do that, right, they also draw the molecule of oil or fatty acid in there too. Okay? And so the fatty acid's happy because it's inside, surrounded by all the fatty tails of the sodium dodecyl sulfate, or the soap, right? And then outside of it, right, it has the polar group that's happy in water, so then it dissolves the oil, right? So while the oil molecule is sitting inside of this thing called a micelle, which is quite literally a whole bunch of fatty acid tails, right, all around, and then on outside of that is a whole bunch of polar groups, right? It's protected in there. And so now it can dissolve, because water can dissolve the outside of the molecule and the rest of it can go along too, and it's being protected, right? But through hydrophobic effect, right? The oil is, because it's surrounded by all the carbon chain tails that are on there, right? So that's how soap works, right? And you know this very well too, because this is the same principle of how the phospholipid bilayer works in your cells, right? But instead of it being a micelle where all the chains are inside, right, of the nonpolar environment in here, right? And then all the polar environment that's water friendly is out here, right? In a in a phospholipid bilayer, right? The phospholipids form the bilayer by going end on end with each other, with the fatty acid tails on end pointed at each other, like so. All right, so now let's start the molecular representations chapter, chapter 2. A lot of this will be review because we talked about it in the general chemistry part, but it's going to have a more organic chemistry kind of flow to it, or flair to it, as it were. So we talked about this before. There are many ways to represent molecules. We have the Lewis structure. We have the partially condensed structure. We have the condensed structure and the molecular formula. So the question is, like, when you draw these things, right, you have a couple questions to ask. What's the one that gives you the most information, but what's the one that's more easy to draw? Turns out these formulas here don't give you much at all, right? But these, especially the molecular formula, doesn't give you much at all. But drawing out these structures actually do give you a lot of information about conductivity, right? You can't tell the difference between the isomers of the molecular formula, but if you look at these partially drawn and Lewis structures, you can, okay? So, and I just said this a second ago, notice that the molecular formula would be inadequate to distinguish between propanol and isopropanol, right? So, yeah, so this is propanol right here, right? And this is isopropanol right here, right? And this is the same as this. But you would never know the difference if you saw that, right? And we're just going to keep on talking about propanol here? No, I'm just kidding. So, and when you look at isopropanol here, and we have propanol here, right, you can see that in the structure there are different molecules. Isopropanol you can actually use to be like a disinfectant and stuff. You know, we know all about that from COVID times, right? But propanol is completely different, right? And then we have dimethyl ethyl ether here, which has got the same formula, right? So you would never be able to tell the difference. So use Skill Builder 2.1 to practice converting structures, okay? So our friend amoxicillin again, okay? We talked about amoxicillin at length, you know, the antibiotic at length in the last lecture, but the point of this slide is just to say that it's too impractical to represent a compound like amoxicillin because of how big it is, its size, okay? But if you had the formula, it wouldn't tell you very much about what was going on as far as structure goes, and that's important, right? So us as organic chemists, what do we like to do? We like to turn the Lewis structure into the bond-line structure, which we talked about in the last lecture. I also call it the line-angle structure. I don't know why they call it the bond structure. Maybe I'm wrong, but I call it the line-angle structure. Okay, so this is the line-angle structure of the antibiotic amoxicillin. Remember I was talking about the beta-lactam ring there that makes it super active when it's an antibiotic, you know, attacking the inhibiting the growth of a bacterial cell. Remember that? So, I'll just make sure that I've already covered this. Again, this is the amoxicillin, and it is critical to know how to draw these structures for any compound without difficulty to succeed in any organic chemistry class. Thanks for stating the obvious, whoever wrote this, right? Anyway. And that's what I was trying to get to here. So remember when I talked about it in the last lecture, you know, each corner or endpoint represents a carbon atom, right? So there's carbon 1, 2, 3, 4, 5, and 6. And then the same thing here, even with the double bonds, right? Each endpoint or each point and endpoint is a carbon atom, right? And then to bring in hybridization with that, right? Usually we do zigzags for both sp3 and we do for sp2 carbons, right? But when we have an sp hybridized carbon, or any atom for that matter, we draw it as a straight line now, right? No longer a zigzag or angled. Maybe that's why they call it bond line, right? Yeah, maybe that's why they call it bond line, because it's not always an angle. Mind blown. Anyway, just remember, you have something with a triple bond on it, or the sp hybridized, right? It's going to be drawn straight. Whereas if it's sp3 or sp2 hybridized, it's going to be drawn as line angle. Okay. So carbon atoms are not labeled, but a carbon atom is assumed to be located at every corner and every endpoint on the zigzag. Just a little review right there. And hydrogen bonds are also not drawn. Remember, they're implied. Absent any kind of charge or any kind of other notation, like a lone pair or something like that, you assume that there's a hydrogen atom there if it's a tetravalent, carbon or whatever. Right? Let's flog this dead horse even further here, right? We have here this endpoint here. We know that there are two hydrogens there because carbon is tetravalent, right? Again, carbon is tetravalent. There's two hydrogens there because there's already two bonds there. One bond there with that carbon, so the other three must be hydrogens, right? Yes, flogging this dead horse. Hydrogen atoms are not shown, but it is assumed that they are enough to complete the octet, 4 bonds for each carbon, okay? So this is just some practice here, right? You can practice on Skill Builder in Skill Builder 2.2 in Wiley Plus, right? Draw some bond line structures, okay? But you can see here where all the carbons are. They're at each of the endpoints, and wherever there's not a bond to a carbon, it's missing its octet to make a full octet. That's where hydrogen is, absent any other notation or charges, right? Same thing is true of this guy here, right? We have hydrogens coming off of here, hydrogens coming off of here. There's a hydrogen there. There's two hydrogens there. There's one hydrogen there, two hydrogens there, two hydrogens there. There are three hydrogens there, and then one hydrogen there. Is that everything? Let me know in the comments if I've missed anything. Oh, you can't even see because my head's blocking it, so you'll never even know. So, Rule 1, sp2 and sp3 hybridized atoms are in a straight chain should be drawn in a zigzag format. So this guy right here, butane, like that. Rule 2, when drawing double bonds, draw all bonds as far apart as possible, which kind of makes sense too, because remember I was talking about this being 120 degrees, and this being 120 degrees, and this being 120 degrees. So you should draw your bonds that same way. You should not draw it like this because that's so stupid. It looks stupid. Okay, don't do that. Bad. He says bad. I'll put a frown face there too. Don't draw it like that. Okay? But when you're drawing single bonds, it doesn't really matter. You can just draw it any way you want. This and this are the same. Right? I was going to say also, though, if you have like other moieties on there and it's like big and there's like hindrance and stuff, you could draw it so that they're farther away from each other too. But in the end, these two are the same thing when it comes to single bonds. Okay, rule 4. All heteroatoms other than carbon atoms and hydrogen atoms must be drawn, as well as the hydrogen atoms that are attached to them, right? So if it's not a carbon and not a hydrogen, you have to draw it. So here we have an oxygen right there for the OH. Okay. So when you draw the line angle, you draw the carbon chain part like you would normally draw it, but then you also add on its OH part right there. Always add in the oxygen right there. And then since this hydrogen here is connected to a heteroatom, hetero means anything other than hydrogen and carbon, you have to draw out the H part as well. Okay. Makes sense? And then the cardinal rule, yes, the cardinal rule. Never draw more than 4 bonds to a carbon atom. Recall the octet rule. I had this one guy in class when I was teaching a while back. I asked him how many bonds carbon can form, and he was like 12. I'm like, no. So, don't do that. This is the same guy that thought that water was blue. That's a story for another time, though. So that brings us to identifying functional groups, okay? Because in organic chemistry, right, when you have these different bonds forming these different compounds, right, oh, sorry, not different compounds, different structures. Um, you, the vast majority of them that react, right? They react because they're a part of these things called functional groups, and these functional groups are actually known structures that we can memorize. Okay, so just I guess a quick little example here. We have a reaction here where this molecule here, which I don't know the name of, is being reduced by a catalyst and hydrogen gas, and you get that there, right? And it's kind of hard to tell what's going on there, but there's a double bond here, and that double bond just got reduced to a single bond here, right? But when you draw out the molecule here, you can see that this double bond got reduced to this single bond here, right? Because the hydrogen gas and platinum did a reduction. And that makes sense too, because whenever you're looking at a double bond, what is actually happening? It's happening because those two carbons are missing enough electrons, right? So that they can have full octets. So they have to form a double bond so they can share electrons, right? But what happens? What is a reduction? Well, hydrogen gas can do a reduction with the help of a catalyst, platinum, right? And a reduction is quite literally what? Adding on electrons, right? Oxidation is losing electrons. Reduction is gaining electrons, right? So this hydrogen gas here gives an electron to this carbon and gives an electron to that carbon, and thus you lose the double bond because it doesn't need to share anymore, right? Good times. Thank you for making it so I don't have to share my electrons anymore, hydrogen gas and platinum. So when certain atoms are bonded together in specific arrangements and they undergo specific chemical reactions, they can be characterized in these things called functional groups. And I'll tell you now, you need to memorize all the functional groups. You just need to memorize the table 1.2 in your book, but that's this table that's coming up right here. Okay. So here is a table of functional groups. And when you take a quick look here at this thing of functional groups, the first thing to notice here, right, if you didn't already know, the R stands for rest of the molecule. Stands for rest of the molecule, okay? So the functional group will always be attached to an R, which is the rest of the molecule. So in this case, the first functional group we have is called the alkyl halide, right? And alkyl halides are exactly what they sound like. They're an X, which means it can be any kind of halide or halogen, bromine, iodine, chlorine, fluorine even, right? And so that is an example of an alkyl halide there, and propyl chloride, right? And propyl chloride. See, this is why I got confused. They're calling this N-propyl chloride there, or propyl chloride, but then over there they're calling it like chloromethane first. I mean, I guess it just matters how you got taught it, right? So in my class, you're allowed to call it either methyl chloride or you can call it chloromethane. Okay, I'm okay with it. So when you see an X there, you know that's an alkyl halide, right? The next functional group is an alkene. An alkene, like I've alluded to before, is quite literally a double bond carbon, right? Carbon to another carbon, okay? And it's connected to 4 rest of the molecules. But the thing that you need to know and remember is that an alkene is a double bonded carbon to another carbon. Then we have an alkyne, triple bonded carbon to another carbon, right? And it only has 2 rest of the molecules on either side. So an example there of an alkyne is 1-butyne. And notice in this line angle drawing where there's no angle right here, right? They have a triple bond there, which is an sp hybridized carbon, and it's drawn straight, right? Another one that we all love, OH, that's an alcohol, right? OH is connected to the rest of the molecule here. That molecule, the rest of the molecule there could be an ethyl, and if it is an ethyl, then it's ethanol, the ethyl alcohol, the one that we all drink. But here in the example, it's actually 1-butanol. Okay. Then we have an ether. An ether is an oxygen that is connected on either side by a rest of the molecule. Okay. And a good example of that is dimethyl ether, a solvent a lot of people use in organic synthesis. Then we have a ketone, right? And a ketone is a carbonyl, which is a carbon double bond to an oxygen with all rest of the molecules on both sides. Okay? So a good example of that is 2-butanone. I keep on saying carbonyl, just so you know, a carbonyl is this. That's a carbonyl, okay? Okay. Then an aldehyde, right? That is a carbonyl attached to a hydrogen on one side and rest of the molecule on the other side. Butanol is an aldehyde, right? Double bonded, a carbonyl right here, hydrogen right there, and then a rest of the molecule right there, right? Then a carboxylic acid, we talked about that a second ago with fatty acids, right? A carboxylic acid is quite literally a carbonyl connected to an OH. That OH right there has an acidic proton. That proton can come off as an acid, right? And then on the other side of the carbonyl is an R group, or a rest of the molecule. An example here would be pentanoic acid. All right, 5 carbons connected to a carboxylic acid. Okay. Then we have an acyl halide, which is quite literally a carbonyl with a halide on one side and the rest of the molecule on the other one. An example of that would be acetyl chloride. And then we have an anhydride. An anhydride is 2 carbonyls connected to each other with an oxygen, and then 2 rest of the molecules on either side. Acetic anhydride is a very common anhydride. There's more. One of my favorites, the thiol group. It is an R group, or a rest of the molecule that is connected to an SH group. Very similar to an alcohol, right? But it's a thiol because it has a sulfur instead of an oxygen, right? And remember that sulfur and oxygen actually have the same valence number of electrons, right? Because they're in the same group, group 6 of the product table, right? So 6 valence electrons. But the difference is that sulfur can actually have an expanded octet because it's in the next row of the product table. So they use 1-butane thiol there as their example, but there's another molecule called dithiol-3-etol, right, which has 2 thiols on it, right? That's named after, has the name Cleland's reagent, right? And Cleland's reagent is a reducing compound that will reduce disulfide bonds in proteins. The guy who named Cleland's reagent, who the reagent is named after, is named Mo Cleland, right? And he is actually my academic grandfather. It's crazy, right? Mo Cleland of Cleland's reagent, the father of modern enzyme kinetics, right, is my academic grandfather. What that means is that he was the PhD advisor to my PhD advisor, right? So in academic pedigree or family parlance, right, he is my PhD advisor's father. It's great stuff. Let me tell you, there's some high standards when you have that kind of academic pedigree. We have the sulfide next, right, where we have a sulfur and then 2 R groups on each side. Dimethyl sulfide is a good example there. Then we have an aromatic right here, which is basically a benzene ring or a phenyl, right? We have double bonds on every other bond of this cyclohexane, but it's a benzene because it has double bonds in it, right? On every other bond. Then we have the ester, which is very similar to the carboxylic acid, except that instead of having an H there that can come off as a proton to be an acid, right? It's another rest of the molecule, so it's not going to be acidic. Example there would be ethyl acetate. Then we have the amide. This time there's a carbonyl and a nitrogen with 2 R groups. So the important thing here is that the amide group is a carbonyl with a nitrogen bonded to it, right? And the importance of amides is that amides are actually what peptide bonds are made of. And peptide bonds are what link 2 amino acids to each other, and all the rest of those amino acids to each other as well, to form a polypeptide chain, which is the primary structure of a protein that will turn into a secondary structure that will make all the alpha helices and beta sheets and all that stuff of a protein or enzyme functional. And then those fold to become a tertiary structure of a protein and enzyme. And that is the functional unit of proteins and enzymes. Then we have the amine, which you've seen the amine before because it looks a lot like ammonia, right? Except that instead of having hydrogens all around it, the nitrogen right there, it's got R groups all around it, right? So a good example of that is dimethylamine. So you can go to conceptual checkpoint 2.7 to label some functional groups. I don't know if that's in Wiley Plus or in your textbook. I can't remember. But 2.7, take a gander. So let's talk about some formal charges of the carbons then in these different scenarios. Okay, these different scenarios. We know that carbon can only have 4 bonds, right? Can only have 4 bonds. But whenever there is 3 bonds to a carbon, right, and there's no lone pair, that's known as a carbocation, right? So these are all carbocations. There's a +1 charge on a carbocation. It makes sense because cations on the periodic table have what? Positive charges. Okay? But if there is a lone pair present and there's only 3 bonds, we call them carbanions, right? We call them carbanions. Now, the chemical distinction between a carbanion, not charge distinction, but chemical distinction between a carbanion and a carbocation, is that a carbocation has 1 empty orbital, which makes sense. That's why it's got a positive charge. It's missing an electron. Whereas carbanions have no empty orbitals, right? And that's why it's got a negative charge. Negative charge. So let's do some practice with some formal charges here, right? I'm gonna have to I have to hide my head so you can see this entire molecule, right? So this is an interesting structure. It's great, except that it's missing all kinds of formal charges, right? So let's start out with this guy right here. This is an oxygen, right? And remember, oxygen usually looks like this when it's bonded to something, right? Either like that or in the carbonyl form, like this. And it has 2 electron lone pairs there, right? In both cases, 2 electron lone pairs. Okay? But when you look at this oxygen right here, it's only got a single bond connected to it, right? And it's got 3 lone pairs. Well, that's weird, right? Well, what that means is then that this guy has 1 extra electron. It's got a negative charge. Its formal charge is negative. Okay? And the reason why its formal charge is negative is because usually that 3rd lone pair would be participating in a bond, right? And if it was participating in a double bond, like it would be in a carbonyl, right? It would be using one of its electrons to make it neutral, and the other electron would be with the other atom. That's why it's neutral. Okay? And the example of that would be the oxygen right next to it. That guy is neutral. Okay? We know that, for example, nitrogen here is trivalent, but there's 4 bonds to that, which means it's using one of its lone pair electrons, right, to make a bond, right? That's not good, because what that means then is that it's no longer neutral. It was neutral before, right? Like the one right next to it, when it was trivalent with 3 bonds. So if this nitrogen gave up one of its electrons, right, to form that 4th bond, that means then this nitrogen is positive as far as formal charge goes. Okay. Man, look at this oxygen over here. I mean, that's a lot of bonds to an oxygen, right? And not enough lone pairs. It took one of its lone pairs, just like the nitrogen did, right, to form an extra bond, which means it also has a positive, right? You might be asking yourself, is there an easier way to just look at these things and calculate the formal charges without having actually knowing it by looking at the structure, right? Well, we can do that example with the sulfur here. Okay. So formal charge equals the uh, the lost my train of thought. Yes, here we go. Formal charge equals the valence electrons minus the unbonded electrons right? I'm trying to make it small so that everything fits. Minus half of the bonded electrons. Okay, bonded electrons. So let's do the formal charge of sulfur here, right? So sulfur, right? First, valence electrons. Remember I said before that sulfur has is in the same group as oxygen, which is group 6, 6A. So it has 6 electrons, right? Let's look at this molecule here and see how many unbonded pairs it has. It's got one unbonded pair right there, right? But it's one unbonded pair, but how many unbonded electrons? It's 2 of them. So you minus 2. 2 unbonded electrons, right? And then 1/2 of the bonded electrons. So there are 1, 2, 3, 4 bonds there. Each bond has 2 electrons, right? So that's 8. I don't know why I put 4 there. It should be 1/2. There we go. 8, right? So you calculate all that out, and you end up with 0, right? Because 6 minus 2 is 4, minus 8 divided by 2 is 4, equals 0. So the formal charge on here, on the sulfur, is neutral. And that formula works for everything to figure out what the formal charge is, okay? Formal charge equals valence electrons minus unbonded electrons minus 1/2 of all the bonded electrons, okay? I'm going to come back now because I want you to see me as I'm teaching here, right? So this is just showing you how to draw things, right? When you see it in the line angle, right, and an oxygen has a minus charge, you can already assume then that this minus charge is due to the fact that this oxygen has 3 lone pairs. Okay, 3 lone pairs. That makes sense, right? That makes sense. So that you can use that for nitrogens too, or sulfurs, because it's not absolutely important that you draw out the lone pairs on them in a line angle, but it is important that you show the charge, the formal charge, if it has one, on the line angle. All right. So let's take a look at the different formal charges of oxygen here, right? We did it with carbon a second ago, and I already did it with oxygen a second ago too in that big molecule example. But let's just look at it here real quick, okay? So when oxygen has 7 valence electrons, right? 1 in a bond, 3 lone pairs, right? It's got a negative charge. That makes sense, okay? It has no charge when it has 6 valence electrons, which makes sense because it's in group 6, right? That means 2 bonds and 2 lone pairs, right? So that can be in the form of the ethanol right here, or it could be in the form of a carbonyl right there with the 2 lone pairs up there, right? And then lastly, if you count up the valence electrons and oxygen only has 5, that means 3 bonds and 1 lone pair, right? Like that. It's got a positive charge. Okay? It's got a positive charge. So that also looks like this, since my head's blocking it. And you just got to remember to draw the positive sign right there, right? You know what? My lines are so thick you can't even see what that is. So we'll just go ahead and show you what that looks like. There it is. See? This guy right here. That guy is that guy. Okay? Cool. Well, I guess you could, because I'm posting these on PowerPoint. I mean, on these PowerPoints on Blackboard, so you can see what it is, even if my head's blocking it. Right, let's do formal charges for nitrogen now. So, if nitrogen has 6 valence electrons, when you count it up, that means two bonds and 2 lone pairs, right? Then it has a negative charge, like that. If it has 5 valence electrons, which has no charge, which makes sense because it's in group 5. That's 3 bonds and 1 lone pair. That's what it's usually at, right? That's what it looks like, and it's got no charge. And then when it has 4 valence electrons, it's actually missing some lone pairs, which means it has 4 bonds and 0 lone pairs, right? And so it gives it a positive charge, which is basically everything I showed you on that bigger molecule before, but it's just all laid out here for you to learn and memorize, right? Practice with Skill Builder 2.5, identifying lone pairs. Ooh, I think this actually is we're coming to the end of this this particular lecture here. Maybe a couple more slides left. So when we're drawing line angle structures or line bond structures, I'm gonna always call it line angle, right? You still have to be able to differentiate between the 3-dimensionality of the molecule. Because, as I said before, a lot of people think these things are flat or the electrons are just kind of in spheres, right? But these are 3-dimensional things that have like space. They have a front, back, side, left, and right, right? And so when you look at line angle drawing, for example, this acyclic right here, okay? When you have a solid bond triangle, right? A triangle that's solid, that means that this chlorine here is actually going out towards you. I don't know how to draw that, so it looks like it's going towards me. But it's going towards me, right? But when it has a dashed triangle, it's actually going back into the paper, okay? And then the rest of this here, the carbon chain, is flat, going from left to right. So looking at a cyclic ring right here, or a cyclic ring, a cyclic ring, potato, right? Again, this ring here, this cyclohexane ring right here, is flat in the paper. But the wedge or triangle that's solid is coming towards you, or towards me, but the dashed wedge is going into the paper, okay? And then we have bicyclic rings, or 2 rings, right? And one ring here is the cyclopentane right here, right? And the front edge of the cyclopentane right here is solid and wedged. That means it's coming out at you, right? Whereas the cyclohexane part is flat in the paper. Bromine here, solid wedge, means that it's coming out at you. Whereas this dash here, for this methyl group, right, that's a methyl group at the end there. Remember, we assume that there's, absent any charge or notation, right, we assume it's a carbon and it's got hydrogens attached to it. It's dashed, which means it's going back into the paper, right, not coming out at you. So that's what that means for dashed wedges, dashes and wedges, okay? We can take this a little further here. We have this thing called the Fisher projection. Usually we use Fisher projections for sugars, right? We also use Haworth projections for sugars as well, right? You can actually, this isn't the same molecule, but you can actually cyclize a Fisher projection to make a Haworth projection when you're talking about cyclizing sugars, like cyclizing a hexose, right? But the important part for this, for the purposes of this slide, is that this right here is the wedged part that's solid, and it's coming out at you. Okay? It's coming out at you. Which means this part here, it's not dashed, but it's going into the back of the paper. Right? Because that's a flat cyclopentane pentane right there, or hexane right there, right? You can also draw a bicyclic like this too, right? Where you can see that there's this molecule here, right? Not molecule, but this section of the molecule here, this cycle here that has 1, 2, 3, 4, 5 cyclopentane there, right? And then you still have the cyclohexane there, right? The shape of the compound governs how it interacts biologically, so it is important to accurately depict the 3D and interpret the 3D, interpret 3D and bond line structures, right? That's what I was talking about sugars before, because these generally are, you use these in sugars when you're learning about sugars and like biochemistry and stuff like that. Wow, and that ends today's lecture. So today will be the first time something is due, or something's been assigned, right? Due by tomorrow at 7:59 a.m. That's June 3rd, 2021. Will be quiz 1 and a review of, and the assignment for the review of general chemistry, right? The Blackboard assignment. And I know that we did part of review of general chemistry today in this lecture, right? But you are allowed to watch this lecture first and then do the assignment. That's okay. Okay. Hell, you can watch this lecture first and do the quiz too, because you might be worried that maybe some of the material from the from today's lecture might be on the quiz because we didn't cover it till today, right? But remember when I say that a quiz will only be over the previous lecture, right? So even if we had material that was split in half from one day to the other, the quiz from that day will only be from the previous lecture. So you never have to worry about that. That being said, you can always watch the lecture ahead of time because you have 24 hours to do these things, right? 8 a.m. is when it's posted, and then it will be closed by 7:59 a.m. the next day, right? 24 hours. It has to close at that time because at 8 o'clock the new ones get posted, okay? And just a reminder, exam 1 is on Friday, June 4th. Hope you enjoyed the lecture. I'll see you tomorrow.